So here we have a step-by-step guide of how to solve problem 2, 1a and b, or as it's called in Holmes, problem 1, 2, a and b. So let's just consider the first one, a, where we are asked to find the truncation error of a finite difference formula given by this expression here. Now, what do we notice? Well, first and foremost, we should remind ourselves what j plus 1 means and what j minus 1 means. On the index, we should see for ourselves some kind of time axis where we have tj here and tj minus 1 here and tj plus 1 here, and where the distance between time points is given by, for example, a step size k. And the reason why I would like you guys to be able to visualize this each time you see a finite difference formula is because that way we demystify a lot of the notation, because instead of just seeing a jumble of letters, then actually what you're saying is what these letters stand for. Okay, so how do I find the truncation error in this expression here? Well, actually we are asked to find the order of the truncation error, but since, so we're actually asked to find the order of the truncation error. But in order to do that, we have to find the truncation error first. Now, what is the truncation error? The truncation error is the term that we remove from an exact Taylor expression of the derivative of y in order to obtain a finite difference method. So what we do when we find the truncation error here is we use the approach that we find in Holmes. So we are inspired by the approach in the book. So we use the approach in Holmes, equation 123 to 128. And if you're not sure which equations I'm talking about, they are on page 6. And I would recommend you just quickly read that section again if you can't remember what's in that section. So we use this approach in reverse. So in this section, we are told how to approximate y prime using some kind of Taylor expansion, and then we have an exact expression of y prime with something Taylor related and a truncation term, and then they go on to find a finite difference scheme called the forward Euler method by removing that truncation term. Now what we want to do in this exercise is go back and find what the truncation term is in this expression here. Now how do we do that? Well, let's just start with step 1. Isolate Fj such that we have an equation where we have Fj on the left-hand side and all this other stuff on the right-hand side. Because in the end, the truncation term is the difference between our finite difference approximation of y prime, which is exactly Fj of y prime and Tj, and our exact value of y prime and Tj. So we start by isolating Fj such that we have Fj on one side and everything else on the right-hand side. Now, step 2. Then, as I said before, our truncation error at time tj, so our truncation error tau j is equal to y prime of tj, and then minus the approximation here, minus the right-hand side, where we make the following substitutions. Where we substitute yj in this right-hand side expression by y of tj, so by the exact value instead, and where we substitute yj plus 1 by, well, you've guessed it, since I spent so much time on explaining that tj plus 1 is just tj plus k up here, this is tj plus k, and where we also substitute fj minus 1 by the exact expression y prime of tj minus k. Now, why is it that I can do this? Why do I just substitute the exact expression in here? Well, it is actually because that is how we use these steps in Holmes in reverse, because when we first try to do a Taylor expansion of y prime of tj, we get some terms that are Taylor related and a truncation term, and that is the first step towards making a finite difference method. And then afterwards we say we remove the truncation term, and then we substitute the exact expressions with the approximations. And so that's what goes on in the book on page 6. So when we want to go backwards, aka find the truncation error by using the expression for the finite difference formula, then we make the substitution the other way around. So we say, well, let's pretend that these are given by the exact expressions. What then is the error tau j? So after we substitute these things into the right-hand side here, we will have an expression that involves y of tj plus k and y prime of tj minus k, which leads us on to step 3, which is Taylor expansion. And in the first part of this exercise in A, what's interesting for us is how we can use Taylor to find an expression of y in tj plus k and find an expression of y prime in tj minus k. So what we want to do is Taylor expand two functions. So we want to expand y by doing the expansion around tj and evaluating in, well, you guessed it, tj plus k. And I guess that if we go up to order 3 for the remainder, that should be good. And also we want to expand y prime, because we also want a Taylor expansion of y prime, so that we can write this using some Taylor expression. So expand y prime in tj, and where do we evaluate that Taylor expansion? Well, we evaluate it in tj minus k, because that's where we want to evaluate y prime, and also to the third order. Now note, because here we're expanding y prime, when I say that we're doing a Taylor expansion of order 3, that means that the remainder includes the term y differentiated 4 times and not just 3 times, because the 0th order is y prime and not just y. So after I've done the Taylor expansions, then I can substitute my Taylor expansions into the expression for the right-hand side, where I remember that the remainder I have here, which is most likely something to do with y differentiated 3 times in some point e to 1, is not the same remainder as I have here, which is y differentiated 4 times and some point eta 2. So remember that these etas do not coincide either, because we're talking about two different Taylor expansions evaluated in two different points. So after I do this, then there's a lot of calculations involved, which you guys are probably better at than I am. And you will arrive at some expression for tau j that is, well, we still have the y prime of tj from here. And all of this that you have on the right-hand side will have to be subtracted from here. And then you will get an expression of k. And you are supposed to arrive at the conclusion that this has the same order of magnitude as h squared in A. And in part B, you just do exactly the same. But instead of doing these two exact Taylor expansions, you have to expand y in tj and evaluate in tj plus k and tj minus k respectively instead, because of the way the finite difference method is constructed. And also in part B, you should arrive at the conclusion that the truncation error is big O of h. So this is more or less a walkthrough of how you do the first exercise. You will probably run into problems anyways, because there are a lot of Taylor expansions involved and a lot of calculations involved, which in turn means that there are a lot of mistakes involved. But don't hesitate to ask, and also remember that there is a PDF file with an example that I have uploaded on the Epsilon page.